Welcome. In this video we are going to present 3DExpress, the new software product from AQSense. 3DExpress is a preprocessing software for machine vision applications that includes graphical assistance for the configuration and debugging of 3D acquisition systems. To explain that program, we will present a use case in which we want to analyze some features of a piece with an inclined plane. On the screen you can see the system already configured. As you can see, we have an input, which is a camera 2D, and two configured outputs, a Z map and a range map. You can see the picture of the Z map displayed, which is refreshing already from the acquisition system. On the screen, you can see how an already configured system looks like. So let's start by describing a bit the interface. Right at the top, you have a list of the configured cameras. Right now we only have a 2D camera configured, listed as camera 0. So you can see there are some stats of this camera, like the frames per second and range maps per minute. Right below, we have a list of the outputs configured for each camera. We can now see that we have a Z map and a range map configured for this camera 0. Also, you can see that there are some stats for each of the outputs. Finally, at the bottom of the screen, you can see a log. Here you will see a report of the activity that affects the server. So let's start from the beginning and see how we would configure a system like this. First of all, I'm going to close this program. And we run a new instance. That, as you can see, it starts from 0, from an empty configuration. The first thing we should do is configure the new input. We select it from the menu and we are presented with a wizard in which we can choose, first of all, the type of the camera that we have. As we have explained, in our example we use a 2D camera, but here we could also select other types of cameras. For example, we support the photon focus 3D camera or the one from Automation Technologies. For our purpose, we will choose the 2D camera. On the next step, we have to select the driver that we're going to use. This is going to depend on our setup. For our case, we have a 2D camera connected with camera link to a silicon solver frame grabber. We can choose it from the drop-down list. So we can see now we have a lot of parameters that we can fill in with our desired configuration. For our case, we only need the configuration file, which we have previously configured for this specific test. Let's choose it. This will be enough for this test. To specify any additional option, we only have to select it and fill it with our desired value. In our case, however, this is not needed. So let's just unselect and proceed to the following step. As we have a 2D camera, the next step is to configure the peak finder. As you can see, when we press next, the program asks us if we want to see live image. In this case, we select that yes, we want to see it. Okay. In our system, I have put the calibration pattern that we will use later to calibrate the metric configuration. So what we are seeing here is the laser projected on this pattern. 3DExpress comes with a peak finder based on center of gravity. But if you also have a valid license, you can choose the peak finder from Salt3D. You can select it from the drop-down list. For our purpose, here we are going to keep on using the center of gravity one. The next thing that we have to choose here is the threshold appropriate for our acquisition system. As we can see in the live image, the sides of the pattern are not correctly detected because our threshold is set too high. So we can zoom in this frame using the mouse wheel, and we will see the values of each pixel. As you can see, the values of the background are below 20, while the values of the detected laser are almost above, around 40 or 50. So here a good value would be around 30 or 40 for the threshold. Let's say 35. We can zoom out now and we will see that all the pattern is correctly detected now. The last thing that we can specify here is the number of threads that we're going to use for the peak finder. This is going to be useful, especially in cases where we have to deal with a high number of frames per second. So, if we want to ensure that we're not losing frames, we can increase the resources of the computer that we're destining to this specific task. To do this, we only have to increase this number. Okay, for our case, I think 1 is enough. Now that we have the peak finder configured, the next step is going to be how we determine when a range map starts and when it ends. So we go to the next step. In this screen there are several parameters, but depending on your setup, only some of them are relevant. So let's try to describe them a little bit. First one is the frame time mount. This is especially useful if you have the camera configured in trigger mode. If there is an interval greater than this value between two consecutive triggers, the server will consider that the range map is finished and on the next frame start a new one. Then we have a feature called laser detector. It consists of 3 parameters. The important one is the mean points. If it is set to 0, this feature is not used at all. Otherwise, the server only considers that we are acquiring a range map if there are at least as many valid points as this value set here. So for example, if we set it to 10, unless the laser detector detects 10 points, our new range map is not started. The other 2 parameters specify the first line to be used for this feature and the last line to be used. Finally, we have the maximum number of profiles. This is the maximum length that the range maps can have. So even if we don't receive a timeout, or even if the detector still considers that we are inside the range map, when we reach this value, the range map will finish and we'll receive a new one. Okay, now that we know how to cut the range maps, we'll go to the next step, which is configuring the metric configuration. So let's go to the metric tab. Again, we are presented with a drop-down list. See that for now we have 3 options: metric factors, metric from file, and static metric. First one is the one that we see. It's the one that uses a scalar factor for each of the 3 axes. So here we don't do a projective correction. So we can specify a value that will multiply each value in each axis of the range map. This will create our cloud of points. But let's see how to use the metric static. We choose it in the drop-down list, and we are presented with how we have the setup configured. Right at the top, we have a representation of the pattern and the values of each of the points that define it, along with the height. We can use a file that sets these values to the proper ones. Here we're using a pattern which is different from the default one. So we have a file that looks like this. You can see that there are the 4 points and the height. Okay, so we just load points, select the file, and we can see that the points are loaded along with the height. Okay, let me make this bigger because it hasn't resized properly. Okay, we have the ROI as well, which we won't be using here. Then we have the encoder step. As we're using the static metric, we have to provide this information to the calibration. For our purposes, we have measured this before the acquisition, and we know that this value is 0.2. This should be equivalent. If we have an encoder, for example, it will be the value that the encoder has Or if we are using, as we are now, a free running camera, a good way to measure this is to measure the total length of the pattern and then divide it by the total number of profiles that we know that this pattern has with on a certain acquisition. Okay, finally we can specify a profile number, which will be the profile in a range map that will be used to do the calibration. Here, as we have a static setup for now, we can see that all the patterns look the same, so we just stay with 0. We have the pattern represented here, so we just need to calibrate. But first of all, let me change the encoder step, which I forgot to do before. Also, I should mention that all the measurements that we have here are expressed in millimeters. As we have the pattern, the point of the pattern defined in millimeters, this is the measure that will define the rest of the system. So from now on, all the measures that we see will be expressed in millimeters. Okay, let us calibrate. Okay, here we have the calibration results, pretty good. And here we can see already the pattern reconstructed. Okay, now that we have all the input chain configured, let us add some outputs to see how everything is acquired. So the easy thing to see is the range map that is generated. So we just add a new output, and by default we already have a range map. To do a quick check, this will already be okay. So we just press OK, and here we can see that the system is already grabbing, and we can double click here to check the range map generated. So I told you we still have a static system, so what we see is a range map with all the profiles which are the same. Okay, let us try to test the system to move it, to move the axis, and see how the range map will look. Let's go to the controls and the movement, and we will see. Okay, so here you can see already the shape of the whole pattern. The system is working properly. But let us change the pattern now that we have already calibrated, for a piece that we will use to do some test measurements. This piece has an inclined plane, and it has a hole in this plane. So as a test, we will try to measure the diameter of this hole. To do this, we will align this inclined plane to the Z plane using our tilted Z map, and then we will pass this over to Sherlock to further analyze in 2D. Well, I've already put this test piece on our system, and let us start movement again to see how the range map looks like. Okay, here we see, as this piece is a bit darker, we'll have to increase a bit the exposure time. We can verify the live image, and let's see, as you can see, the top of the plane is barely seen, the image. So okay, much better. Okay, so we already have this piece. As we said, we want to analyze the diameter of this hole in Sherlock, so let us define an output that uses this plane to align this surface to the Z plane, so we can later analyze this radius. Let's close it, stop the acquisition, And well, we can configure this output, and instead of a range map, we select ZMap plain line. Okay, we make it a bit bigger, and here we can select get range map. We can zoom out a bit. Okay, and here we can see that we can set a ROI. So this will be used to choose all the points that fall inside this ROI and take all of them to fit a plane that will be aligned to the Z plane. So we choose something around here. As we have the piece moving in two directions now, we have to make sure that two consecutive, okay, I forgot we are not grabbing now. Let's grab again. We have to make sure that both directions, in both directions we have a valid plane. Okay, looks good. So we can already see how it looks like. Okay, not bad. As you can see, the top plane is already the same color, which means that it has almost the same Z. We can check the values. It's around 0, which is exactly what we wanted. Okay, now that we want to analyze this Z map in Sherlock, we have to activate its frame output, as Sherlock only accepts frames. To do this, we configure again this output, and to generate the frame we only have to select something different than none in this drop-down list. So we choose 8-bit unsigned. Okay, can apply, and we can see that the frame is already generated. The second thing that we want to do is to ensure that both axes have the same resolution. From the calibration, we know that the encoder step is 0.2, so we define 0.2 millimeters for both axes. We hit apply. Okay, now we see that the Z maps already have a better aspect ratio. And the final thing that we want to touch is that we want a fixed output size for each frame, as Sherlock expects that. So we can check here the size of the Z map and the corresponding frame, and to be on the safe side we can use height 210 and width 330, for example, as the height and the width may vary a bit depending on the detected pixels. We hit apply again, and we see that there are some black borders for the profiles and pixels that are not that don't have information, but that's okay. Okay, so we can close that, and it's ready to pass over to Sherlock. So let's try it. Let's open Sherlock. Okay, and we see that we have to increase timeout. This should be okay. See that we are already receiving this properly, and we have an analysis saved. So no, I don't want to save this. Let's open. Okay, so here we have it. Sherlock is already detecting both holes and checking their diameter and the distance between them. We have already a planarity check, which seems to fail sometimes now. It might be related to exposure time or lining conditions. Sometimes it's okay. So here it is. A thing worth noting is that we can also use 3DExpress while Sherlock is running to check the inputs. You can see ZMap is working properly. We can even add new outputs. For example, let's imagine that the ZMap was failing somehow. We can configure input 0 and add a new output, and we want to check how the range map looks like. So you can see that still Sherlock is running, and now we can have a look at the range map without any other process. So you can see now that top plane is of course inclined as a gradient, and everything is working without stop. Aside from the Sherlock plugin that we've just seen, 3DExpress also comes with a C++ API that makes it very easy to interface it with any software that you might have. As an example, we here have crafted a simple example that shows how to use it. As you can see, here we make use of our viewer tool as well, and we will display the ZMap that we have already seen in the previous example. So basically, you just create an instance of ACQ server. You have to specify the number of the output. You can go back to the 3DExpress to check its output number 0. So we started grabbing, and then we start a loop in which we wait for each item, then we get it from the server, and then we flash the output, and we display the item we just grabbed. So let's start it. Okay, and here we have a window displaying the ZMap coming from the server. Again, we can use it. We can see the object in 3DExpress as well. And we will see that both are going. As a final note, in future versions there will also be a .NET API to interface with 3DExpress.